It's my pleasure to welcome everyone back to our special session of difference equations and applications here at the University of Maryland, Baltimore County. It's my pleasure to introduce our first afternoon speaker, Candace Kent from Virginia Commonwealth University, who is going to speak to us on the boundedness of positive solutions of a reciprocal max-type difference equation. So it's been an honor working with her on difference equations since as part of my PhD thesis, creating a lot of ideas together, and this has been an ongoing project with Candace and me for the last 15 years at least. So I'm very happy here to have her speak with us. Let me just cancel.
Sure.
This is.
Oh yeah. Let me get this right. Okay, this is, thank you, Michael. This is joint work with Mike, this particular paper. And it's really on the unboundedness of positive solutions of a difference equation that involves the maximum function and reciprocal arguments. And actually, the maximum equation, its ancestor, long ago, well, in the 90s, came from the Hanon map, and but it's grown and transformed and metamorphosed into all kinds of things. In the next talk, you'll see still another version of this. But here's the maximum function, and K and L are arbitrary delays. We have reciprocal terms, and AN and BN are parameters that are variable. Mostly, in the end, we'll consider them periodic, but in the middle of the talk, they don't necessarily have to be periodic. They can simply be arbitrary. Everything is positive. The initial conditions are positive, so solutions, and AN and BN are positive sequences. And, for example, we in particular had studied Michael Michael and his grad student max equations with K and L that look like this equation, 0 and 1, or this equation, or this equation. Okay, we're going to give not necessary conditions, although in the next talk you're going to see necessary conditions. But sufficient conditions on the not even on the periods necessarily, but on the parameters to be for every solution to be unbounded. Now, with this maximum equation, it is very interesting in that it shows two types of behaviors. It is either such that every solution is unbounded, or every solution is eventually periodic. And really, there are two questions unanswered. What makes things eventually periodic? Even though this talk is about unboundedness, what makes things eventually periodic? The other is actually with the unboundedness, the periodicity, let me just go back, periodicity of the separate arguments, 1 over xn minus k as an equation, or 1 over xn minus l as an equation. If you they are both equations that have periodic solutions from the very beginning. If you put them together and take the maximum, you will find that the average of the periods of each of these is the period, the eventual period of this entire equation. What's going on there? So there are lots of things that are very interesting. But unboundedness is what we'll treat. Now let me just get this straight. Okay, also we're going to introduce the idea of extended periodicity, which is simply the pattern of unboundedness that is seen with subsequences of the solution. There is a pattern that is very interesting with infinity and 0. Okay, so a survey, which probably this talk will mainly be about. Since the early 1990s, the probably the first equation that looks similar to what I'm talking about was this non-autonomous equation, which did exhibit unbounded solutions when the parameters little a and big A were negative, and the initial conditions were real, but non-zero. However, and eventually periodic in other cases. However, with a non-autonomous equation, whoops, oh dear. Okay, with a non-autonomous equation, the first one of its type where one of the numerators was a variable sequence, it was taken to be period 2, and no unbounded solutions were observed. However, when the period was upped, then unbounded solutions were observed when it was up to period 3. And also, not only that, but in a sense, the AN was intertwined with the other numerator, or bounding the other numerator, 1. So there was an extra condition, and the period was important. But upon the discovery that there are unbounded solutions, Mike and I looked at this general equation with AN and BN, periodic with period P and Q respectively, and delay 0 and 1. And we found that essentially solutions, if AN and BN, if neither P nor Q are multiples of 3, then all solutions are bounded. On the other hand, if certain conditions held with the parameters and solutions, and P and Q were multiples of 3, then we did have unbounded solutions. Almost necessary and sufficient conditions. And Mike and his student studied another equation with
You went forward a little bit too far.
Yeah, what am I doing?
Go, just click back.
No,
Click back?
Yeah.
Oh.
Keep clicking back a little bit.
Yeah.
Okay.
You get back there. There you go.
Oh, I went way ahead. Thank you.
Yeah.
Thanks, Dan.
Yeah.
Okay, in any event, this new delay was unbounded if the period of AN or BN were multiples of 4 and if certain other conditions occurred. So, and by the way, with AN and BN replaced by 1, this max equation has solutions that are eventually periodic with 4. So there seems to be some kind of resonance going on, which seems to have biological implications, by the way. Okay, and then there was a seminal paper, I consider it seminal, by Bidwell and Franke at NC State, in which, this was a dissertation in which they showed with an arbitrary number of arguments with the maximum equation with delays going upward, but non-negative parameters, that every solution is, if every solution is bounded, then every solution is eventually periodic. So this brought up the question, well, when are solutions bounded? That will be answered by Dan, sitting there. And not quite. Actually, I'll be asking under what conditions with positive parameters and 2 delays is every solution unbounded. And let's see. Okay, let me just now give some definitions. Boundedness and persistence go together. If you have positive solutions, you're bounded from the top. All terms are bounded by a positive number, and persistence is when positive terms are bounded away from 0. They do go together when AN and BN, those parameters, are periodic. You have one, then you have the other. Okay. And eventually periodic, as I said, was what happens when if you don't have every solution unbounded. Eventually periodic is where you start along with some term, not at the very beginning where you have periodicity, which is very interesting. It's an interesting question in itself. Why does that happen with certain equations, not just the maximum equation, but equations that seem to involve decision making? In our case, we also will talk about extended periodicity in the limit as n tends to infinity when we look at unbounded solutions. And that's when we have subsequences, let's say p subsequent, if we have extended periodicity with period p, then we have p subsequences, some of which go to infinity and some of which go to 0. I'm going to give a important, for this talk, definition that really says it all, or does everything for us. It's a technical definition. But for convenience, I'm going to let t be equal to k plus l plus 2, which happens to be the period, again, of, which happens to be the period of this, our max equation, with 1 in the numerators instead of a, n, and b, n. And such that multiples of this period will lead to unboundedness. Yeah, I did it the right way. Okay, so sufficient condition for unboundedness that we're going to show is based on what I'll call, what everybody calls hypothesis H. And that involves soups and ints and strict inequalities between soups and ints of subsequences of A and B, or B and A, and B and A. Again, the subsequences are intertwined in a sense. Further conditions for extended periodicity involve more of these inequalities. Just many more. K plus 1. And when AN and BN are, I forgot to mention in hypothesis H, AN and BN do not necessarily have to be periodic. When they are periodic, then the hypothesis H turns into something very nice and something not contradictory. The patterns that are formed end up not being contradictory. Things seem to fit exactly, which is kind of interesting. Get this right. Okay, let me move on because how much time do I have actually?
7 minutes.
7 minutes. I'm gonna move it. Okay, I talked about an ansatz. Sufficient conditions for every solution to be unbounded. So we have AN and BN, a pair of sequences that of positive real numbers that satisfy hypothesis H. Don't necessarily have to be periodic. If that's the case, then every solution is unbounded. And the proof is very, very, very simple. Involves looking at the equation, starting with the term x t, that's k plus l, the two delays, plus 2 times n plus 1 and n plus 2. Ignore the I. And we break down the denominators, iterate backwards, then flip the denominators into nins, get rid of some terms, except for those that contain n plus 2, which is in the same subsequence as the what this is all equal to. Get a less than or equal to a maximum of an A and a B and an A times the xtn plus 2i term. And we end up, sure enough, with a whistle. Excuse my whistle. We end up with a reciprocal of the soup that we were talking about being strictly less than the inf of a subsequence of B, a subsequence of A. And this term here, the maximum of this term is strictly less than 1. And in any event, to make a long story short, we end up with a solution, a subsequence that goes to 0, that where there's lack of persistence. We then take this term and place it in a future term, and we show that it's in the denominator, it goes to 0, the numerator is fixed, and we get a subsequence that goes to infinity. Therefore, our solution is unbounded. We also show what can happen when we, I think I went ahead, yeah. Extended periodicity of positive solutions looks like this when we make the assumption on delays. This is a very restrictive assumption, but when we make that, we can actually make all kinds of assumptions and get all kinds of patterns. But the pattern that we get is that, I don't have it here, but that k plus 1 subsequences go to infinity and or go to 0, and L plus 1 subsequences go to infinity. So we get a 0, 0, 0, 0, infinity, infinity, infinity. On the other hand, with this Mike's and his grad student's equation, which doesn't satisfy this restrictive inequality, and rather gives an alternating 0, infinity pattern of extended periodicity. Then when AN and BN are made periodic, I'm going to skip ahead, all the way ahead, we end up with the case when this restricted condition on the delays, and Bn is periodic sequence of positive real numbers with period, this k plus L plus 2, a multiple of this k plus L plus 2, which is the average of the periods of the arguments in the max function, and we get, we add another condition of the certain subsequences of the BNs bounding all of the periodic the terms that repeat in the AN sequence, and we get every solution is unbounded. We can also do the same for AN being a multiple of the k plus L plus 2 term, and we also get unboundedness. So AN being a multiple of the period. In a sense, there's resonance, we get unboundedness. And I'm going to skip ahead to future goals, which is where my heart is now, in a sense, because planning on writing a paper, a survey in the max equation on the a series of different maximum difference equations and the possible applications. They have none so far, but with this unboundedness nature, or eventually periodic nature, we're going to propose that they either have applications in neuroscience, in particular, for example, in epilepsy. You can imagine epilepsy with seizures, unboundedness, or in what's called morphogenesis, that's embryological development into the complete adult. And when it goes awry, as seen with cancer, where there is no differentiation of cells into specific organs, in other words, things go awry. They're also unboundedness in a sense, and I won't go into, even though my heart is here right now, I won't go into detail, and I think I'm going to stop here early.
Okay, Harold?
You just say a little about this and the Henan map, like you had mentioned that earlier.
Say that again?
You said something about a connection with the Henan map.
Oh, yeah. It's like the Henan map. Ah, let me try to
I wasn't
remember.
familiar with that.
Why, yeah, I know. I have it in my other notes. A change of variable is done with it. It's yn plus 1 equals, and there's the absolute value of, I can't remember.
Absolute values and maxes are related.
And they're related, exactly.
Well, piecewise linear and maxes are because max type originated from piecewise linear. if I'm not mistaken.
Yes, but with
which is piecewise linear is a special case of absolute value.
so that led to a certain max equation that exhibited periodicity immediately from the beginning, period 9. But from that, that's not really, okay, that was interesting, but from that blossomed or evolved these max equations that did more and more things, and then there were equations with a minimum function, with what's called a ranked function, and different arguments, and all these decision-making types of equations that lead to this eventual periodicity.